I will give you all the equations you've gotten all semester. Yep, that will not change. Okay, guys, the objectives: define and apply two types of potential energy. So let's start by talking about what potential energy is. Pick an object that's sitting on your desk right now. Any object that's sitting there. And while it's sitting on the desk, it doesn't have potential energy.
It's got potential energy of gravity.
Cool. It could have potential, right? Could it not have potential? Let's go this way. What has more potential energy? My water bottle that's halfway full or this big ton? Does everybody agree it's a water bottle? Okay, so something that has mass is going to affect its potential energy, right? Now, what has more potential, the water bottle up here, or when I put it right next to the ground? Say higher up. So what else has an impact on potential? The height of it, and by saying it, we'd also say gravity. So the first type of potential energy we're going to talk about is called gravitational. And just like we've gone through right there, there's a couple things that affect it. Brennan, will you close that, please, while we're doing this? Potential energy of gravity is equal to or impacted by the mass of an object, gravity, and the height. There's the first type of potential energy. The second type requires a spring. I don't have the other side of it, so I'm going to see if this will hold.
Seems like a really bad idea.
Bad idea? That is. Seems to be all right. So if I pull down a little bit right here, is there any stored energy in here? Yeah, when I release it's going to shoot up there, right? Right now, is there any stored energy in there? There might be some potential of gravity, but we're talking about a different type now. When we say the further I pull this down, the more and more energy it has to move back up, and maybe if I attach a mass to it, it would launch that mass. So, see if it holds this mass. So right now, if I let go of the mass, is it going to fly? Or is the spring going to move? Yeah, so there's some stored energy. If I don't do anything right now, is the spring going to fly? No. So what do I need to do to put more energy in the system?
Pull down.
Yeah, pull it down, or I can even push it up. But if I pull it down a little bit more, and I release, then it's going to move up and down because there's some potential energy in there. Now, we got to talk about what kind this is and what affects this. So think about, keep in mind this spring that I just moved. And let me get two rubber bands. Let's take a really skinny rubber band. Close your eyes. Oh, no, I'm just kidding right now. What's going to happen if I did? It'd probably break, but let's say that this was so durable that it held it. What's it doing as far as the distance, though, when I put this mass on? Yeah, it gets further and further away. So its relaxed point is going to be a lot lower. Would you agree with that? Okay, if I take a more sturdy rubber band, Cooper.
Yeah.
Miss Wu.
I gotta go home.
She didn't say. She said she needs to see you.
Yes.
You're making
Come on, you want to leave
You're
right
making me
here?
ask for Cooper. Let's go.
Oh, now everybody's all funny. You're nice enough to let him wear it.
What?
Now be quiet. Is this rubber band different than the previous one?
Yes.
It's definitely sturdier, so it holds a little bit different. So let's talk about what affects this type of potential energy. First of all, we're going to call it elastic. Good. We're going to call it elastic potential. And what did you notice affects it? The distance that I pulled it,
I guess the durability.
the durability of the spring. What's the X going to represent?
Durability of the spring.
Careful. What do we always use X for? Distance. We'll call this
The durability.
the distance from relaxed, or better yet, displacement from the relaxed point. And the K, instead of calling it durability, we're going to call it a constant. We're going to call it the spring or force constant.
When you say distance from relaxed being how it's sitting right now.
Yep. We'll talk about relaxed here in a second because there's two types of relaxed.
So is there just a across the board constant you plug in, or is it different for everything?
Different for everything. And we'll determine the force constant on that spring we just looked at in a second. Any questions so far? Okay, really quick, just as a little test here, if I told you the gravitational potential is 100 joules and I gave you the mass of an object, could you find the height it is above the ground?
Yes.
That's pretty straightforward, right? I would give you potential, the mass, you could find the height because gravity is the 9.8. Right? So do we need to do a bunch of practice with that? Probably not a ton. On this side of it, the elastic side, you're going to get things like a K. I might tell you the spring constant is 100 newtons per meter. That's the units on it. 100 newtons per meter. And I might tell you that you pull that spring 0.5 meters. Could you find the elastic potential energy? Yeah, I hope so. Right?
Just one half inch.
Exactly. The other thing that we need to talk about here is this word. Maybe this word if it shows up there. There we go. Arbitrary. Newtons per meter. Spring constant is newtons per meter. The word arbitrary, and this goes back to gravitational potential energy. And what I mean by that, if I draw a little picture here, so here's the ground, here's the desk, here's a bookshelf. You guys with me on that? Okay, I'm going to put a little book or box on that desk there. And if I'm looking for its potential of gravity, does it have any right now?
Yes. Yes.
Okay, it does. What's the height? So let's say I told you that height is 1 meter and the height to the top of the bookshelf is 3 meters. Yeah, so it has a height of 1 if we set what point as our 0 point? Careful. If I say that the ground is 0, then our H is 1. Do you guys agree with that?
So what are we trying to find?
Right now we're looking for the MGH
Of what?
of the book. The book is this thing right there. Okay.
If we're doing that, are we just going to arbitrarily assign the ground as 0?
That's the point here, guys. Hey, I'm using the word arbitrary because we can pick our 0 point. So if I pick the ground as my 0 point, does that thing have potential energy of gravity? It does, because the height would be 1. What if I set my 0 point as the top of the desk? then this would no longer be 0. It would be 1. It would have no potential. I hope you're picking this up.
Yeah.
What if I set my 0 point as the top of the bookshelf? It would have negative potential energy.
So at different points, it has potential energy.
Yeah, it's
So I look here on the ground with potential energy, but on the rest.
right, and it's all about setting an arbitrary reference point.
Is only gravitational arbitrary?
Yeah, gravitational is the only thing that's arbitrary. Do you guys have that down? That idea?
Is that a concept?
That I would say that's a concept. Absolutely, you're going to see a concept question.
So
Just like
we're
that.
just saying this, let's do it as, pretty super gravitational.
It wouldn't, but if I said that the desk is my 0 point, then right on. So it depends on what you
There has to be a distance from the ground.
right. The most convenient arbitrary point is going to be where? The ground, or I'm just going to say the lowest point.
Wait, you can set your height to 0 wherever you want.
You really can. But the most convenient way to do it is our lowest point. Pick the lowest point. So really quick, look at your practice problem sheet that I gave you last class. And I just want to read through number 3.
Which one?
On the back side, guys, where it says potential energy at the top. If I look at number 3, let's read that last line carefully. It says, find the gravitational potential energy associated with the child relative to the child's lowest position. So where does height equal 0 then?
At the bottom of the swing.
At the lowest part of the swing. That's what they're suggesting. In this case, they tell you, find the gravitational potential energy associated with the child relative to the child's lowest position. On other problems, it might not tell you. You're going to have a website problem that talks about a skier. Sometimes it's going to say find the potential energy relative to point A at the very top of the slope, or relative to point B at the very bottom of the slope. So if you're at the bottom, you might have less potential than if you're at the top. If your point A is your 0 point, you might have negative potential energy, is the idea. Yeah, Carter.
With this child thing, they're swinging on swing.
Yeah.
They're counting in the factor variable. Accelerating up the ground and decelerating going away.
Well, gravity, G already takes that into account for it. The MGH accounts for that.
Oh,
So they're a certain height above. Then when they swing down, that lowest point there is our 0 point. Make sense?
yeah.
Okay. Yeah. What's that? We're going to do this problem in a second. When it's horizontal, that means it's at the very top. So it's literally making a parallel to the horizontal. We're going to do one of these in a second. Actually, let's go ahead and let's do 1, 2, and 3, A and C. Go ahead and do those right now. 1, 2, and 3. But on 3, just do A and C. Do those as practice problems. Ready? Go.
I just did X squared and then multiplied by X.
There you go. X squared is the scaffold is inside the scaffold, right?
Oh, did you do 3.5?
What'd you get? What's that?
You said 3A and C?
Yep.
Also, A is when it's actually. So it would be.
Point zero what? Thank you.
What did you get for
Would you say, would you
So she rushes into the ground.
Well, maybe the ground's down here. Hopefully.
It all depends on.
Hopefully it's a little lower.
As long as
You making fun of my art, DF?
As long as your legs
brilliant.
are straight, so you just don't actually touch the ground.
That's very fair.
It's not like.
Let's just assume it's a little, let's assume it's a pendulum. That's ultimately what it is. It's a pendulum.
So you guys said maybe.
How do you stop?
You don't stop.
Yeah, you don't stop, you just keep going. And how do you swing completely horizontal?
How do you what?
How do you end swinging enough so you go completely horizontal?
That, I agree. That's impressive.
I mean, unless they're like, they're solid bars instead of ropes.
It wouldn't, pretty sure it's not possible.
The child would have to use St. Bolt's move to the sea, 784.
784. Guys, really quick, let's just take a look at 1, 2, and 3A and C. Or you guys need a little bit more time? Okay, take your time. Quickly look at this. The K on number 1 is 5.2. To find the X, we've got to take where that spring is, so that when the spring is by itself, whoops, I lost my writing.
You didn't die.
Oh, sorry to hear that, man. I feel terrible for you. If we look at, guys, if we look at the relaxed length of the spring, this is where it would be before it gets pulled down. And then when we put the mass on it, it's stretched down to here. So we need to find this distance. That's our X value. So our X value here is 1.12. 1/2 kx squared gives us 3.26 joules. Number 2, same way. 0.035 is our X. We get 0.031 joules. Any questions on those two? All right, number 3, they say the swing goes all the way horizontal. So when she's all the way up there, the height is 2. 2 times her mass times G is 9.8. So we end up with 784 joules. 3C, the height is 0 because she's at the lowest point. So she has no gravitational potential if that's our relative point. Now I want to look at 3B together. Let's look at 3B together. It says that the rope is making a 30-degree angle with the vertical. So there's the vertical. There's the swing. It's going to make some kind of movement down that way. There's 30 degrees. What? I don't understand what you mean.
When you're swinging, it goes like this.
Yeah.
There's no, like this one.
Well, yeah, she's going to continue to go. Yeah, I just don't care about that part. But what we need to find, guys, is her height, which is that. Do you guys agree with that? That's her height?
Is it just sine?
So we need to get rid of this, right? Of the 2 meters. Would you agree that
Yeah, so
this whole thing is 2 meters? We need to get rid of this part?
it's cosine 30 gives you the height, and then you minus 2 from that.
Yeah, so well, what we'd say is take the full length, which is 2, minus this, what I'll call that L. Minus L gives us our height. And our L here is going to be 2 because the length of the string still is 2. 2 cosine 30 equals our H. What's our H going to come out to there? Two minus 2 cosine 30. What's an H? Did anybody get it?
0.268.
Okay. And then we just take her mass times 9.8 times 0.268, and we end up with how many joules? 105 joules. Okay, we're done with those practice problems. There's one other thing I want to throw into your notes on elastic potential energy. There's one more equation to add in there. It's called Hooke's law, F equals negative kx.
So it's just the force
The force that's put on the spring
equals the negative constant times the resting point.
Yeah, Eddie, we put that away, please. Thanks. Yeah, it's exactly that. We could find the spring constant of this spring. So right now, it's at a relaxed length, and I can take a meter stick and find out. I've got 500 grams here.
That's 500 grams of force, 500 times.
500, or excuse me, this is a 1 kilogram. 1 kilogram is going to drop it from, right now it's at the 46 centimeter mark. This takes it down maybe, let's see, I'll take the whole thing down. 46 down to about, I'll say 76.
So 30.
So what's my X on
X is 30.
0.3? 0.3. So that moved the spring down 0.3. And what's the force I just put on it?
9.8.
9.8 times 1. Yeah, because I put mg on it. That was the force acting on it. Negative kx. Now, what direction is mg?
Down.
Down. So downward, 1 kilogram mass times 9.8 equals negative k times 0.3. So what's the spring constant of that spring? Somebody do that really quick. I need 2 guys, 1.
Total force,
32.66.
32. Total force, all includes mass counter gravity or something that's sort of that name.
Exactly, a mass that'll be placed on a scale like that, or a spring. So the K is 32.67. Really quick, let's talk about what that means. How many newtons is it going to take me to move that spring 1 meter? 32. Dylan, you with me? It's going to take 32 newtons to move that spring 1 meter. Are you following along with that? So the units on that is newtons per meter. So to move this spring, the length of that meter stick, I'm gonna have to use 32 newtons of force. See how that works? Is that gonna change other times of the spring? Does the spring become less or more
No.
elastic? No, it's the elasticity of that spring stays the same the whole time. So that will never change. Once we find it on that spring, it's good to go for that. Yeah.
So this will always be pulling down, and that'll be a force, whatever pulling up.
Right. Could be a force pulling sideways.
Alright, so then just wouldn't.
Right. It would be, maybe I apply a force of 10 newtons and that moves it 0.1 meters.
Alright.
Okay, could have been something like that. Let's finish today with what I think you guys will pick up pretty quick, and this is the conservation of mechanical energy. Mechanical energy is made up of two types of energy that we've just talked about: kinetic energy and also potential energy. And if I hold a book right here and the ground is way down here, that's where H equals 0. And the book's just going to fall, we'll call this point B, that's point A. And then the moment before it hits is point C. Now, keep in mind, I'm holding it at point A. So what's the velocity at point A? What kind of energy would it have at point A? Just potential. What kind of potential? Just gravitational. The only way to have elastic is if it's what? Attached to a spring. So at the very top, all it has is lots of potential energy. As it falls, what happens to the potential energy? It becomes less, so it gets a little smaller. What about the potential energy at the very bottom? There is no potential energy the moment before it hits at point C. What about kinetic energy at the top? Is there any? Why is there not? It's not moving. There's no kinetic. What happens to the kinetic as it goes further down? It gets bigger. At the very bottom, it is the biggest it will be. No, all we have to do is set all the energy at each position equal to the total mechanical energy. And put a little plus sign in between. It's mechanical because it's the only type of energy that's conserved. When we talk about friction, like a friction force is going to turn some of that energy into heat. So that's not conserved in the system. So here's the idea. Mechanical energy at point A is equal to the potential at point A. So I could say mgh at A equals the mechanical energy. At point B, I could say the mgh at B plus 1/2 mvb squared equals the mechanical energy. At the very bottom, 1/2 mvc squared equals the mechanical energy at point C. Mechanical, or 1/2 mv of c squared. Now, if you look at the very top line, I said this is all about conservation of energy. So if we conserve something, what does that mean? We don't what? We don't lose any of it. We're going to keep it. So the mechanical energy at A is what to the mechanical energy at B? Equal. How is it? How does B compare to C? Equal. How does A compare to C? They're equal. So if I want to find out, Carter, give me 1 second. If I want to find out the velocity before it hits the ground, and I know the mass and the height at point A, I could set the mgh at A equal to the 1/2 mvc squared, because that's all the mechanical energy is at C. This says the mechanical energy at A equals the mechanical energy at C. Try the website. I think you guys will find it's not bad at all.